Alright, hello everyone and welcome. So the reason I'm doing a video today is one, I'm not gonna talk for the whole period, and two, I want to give you um a break of me just talking. You can do this lesson at your own pace. Um and it lets me talk to each one of you individually, just to talk about recommendations and check up with all of you. And catch up on makeup work. So this is going to be a self-paced lesson. It's also more friendly for those that are virtual. Um, so we're going to be talking about valence electrons. And as you can see from my subtitle, valence electrons are the whole big reason that we care about electron configuration. So why do we do it? What does it actually matter? And this is kind of just an introduction to that, and also a review of electron configurations, and it's going to combine what we had gone over yesterday in class with electron configurations. So hopefully it will introduce a new way to get the electron configurations, especially the noble gas configurations. Um, all right, so let's go. Just a recap of electron configurations. These boxes that are over here, they represent where the orbitals are electronically. What I mean by that is energetically. It's probably the better word. So our 1s orbital down here is the lowest energy. As you go up, you are increasing the amount of energy required to put an electron in this orbital. So the 4s has a greater energy than the 3p. The 3d orbital has a greater amount of energy than the 4s. And we fill these electrons up with electrons depending on how many electrons are in the atom. For example, carbon has six electrons. I've gone over how to find out how many electrons are in the atom. You should be able to do that. Please, see me if you need help with that. 6 electrons. So we take the first two and we put them in the lowest amount of energy. Fills up our 1s. We have the next two go in the 2s. And now we start filling up our boxes in the 2p. Notice how I did not pair these two electrons up, but they are in two separate boxes. That was one of our rules. And here are where all of these 6 electrons go. And we can write out our electron configuration as such. What we do is we take the orbital, so the 1s orbital, we write how many electrons are in it. 1, 2. We move on. The 2s electrons, there are 2 in there, and then there are 2 electrons in the 2p orbital. That's how we get our electron configuration. Okay? All right. I want to offer a different way of doing this, using what we had gone over in class. Move my camera up so it's out of the way. There's a lot going on this slide, and I want to kind of go through it all. So, how we can do this. I've circled here, or written onto this image, where each one of these orbitals gets filled up. So if we have our 1s, our 2s, and our 2p, just as an example. The order of the electrons and the elements represents the order of these orbitals. That's why there's the first 2 electrons, hydrogen, helium. Just a note that helium is over here normally. And the reason it's over here is for purposes of electron, but it's usually over here for purposes of what we're going to be talking about soon. Alright, so I know it's a little confusing, but normally helium is over in group 18. So helium is not in group 2. So our 1s electrons, hydrogen, helium, 1, 2. Our 2s is going to be these 2 elements, and as we increase the amount of electrons, we're going through our p. So boron over here has 5 electrons. It will have our first electron will be 2p1, will be its last orbital. Carbon, as we saw, will have a 2p2. Nitrogen, filling up another one, 2p3. and so on and so forth until we get to neon, which is 2p6. So we will fill in our electrons. And this will continue until we get to wherever whatever atom we're looking for. And I've labeled each one of these blocks. They are color-coded and labeled with what orbital that electrons, or those atoms that are filled by electrons, are representing. Alright, so I've done tin. I've circled tin over here. This is, there are 50 electrons in tin. Its atomic number is 50. Can't tell it out by the picture, but it's 50, I promise, because 49 is over here. So tin has 50 electrons. Now, instead of doing all these boxes, filling them up, counting out 50, here's what we can do. We can skip that and start by saying, here's 10, it's all the way down here. Which means that everything above it and to the left of it, all of this stuff that I am circling right now, we know it's probably full. It is filled. So, take our 1s2, our 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, our 5s2. Those are all already filled, just based off of... Oh, forgot the 4d10. Excuse me. Those are already filled. We know that because every single element below 10 that has a atomic number less than 50 will have those electrons filling up one by one. And we are now in the 5p block here. So indium would have 1, 5p1. Tin will now have 5p2. It's the second element in this 5p block. And we know that we would go up to 5p2, and this whole thing right here is the electron configuration of tin. Alright. Noble gas configurations. I think what I'm going to show you will make this a little bit more clear. Hopefully it does. We talked a lot yesterday about the noble gases, and I'm using the term now just because I've introduced it. They are the elements in group 18, so I don't show all of them here, but helium, neon, argon, below that's krypton and xenon. Those are the noble gases. They are all the way off to the right in group 18. What we did previously is we took the electron configuration of the noble gas in the period above the element we were talking about. So here's carbon. Carbon is in period 2. Helium is in period 1. So carbon, the noble gas, up one row and all the way to the right, up a period, and in group 18 would be helium. So here is carbon's electron configuration. Here is helium's. So all we do is take the 1s2, we cancel it out, and we are just left with this 2s2, 2p2. And we would get this as our electron configuration in the noble gas form. Alright? And I'll get to why this is important soon. So that is the noble gas configuration. That's how we had previously done it. I had given you the electron configurations of the noble gases. I gave you a table that had all of them. Here's another way to do this. And I'm going to do this with 10. So you still want to find 10, which over here, circled. And you still want to find that electron, or the noble gas that is up one row and all the way to the right. So we go up one row, up a period, from period 5 to period 4, all the way to the right, we find krypton. I'm going to write this out in krypton, in brackets. So all of this stuff, all of these electrons we don't care about now, because we've now crossed them out with krypton. Now, all we have to do is everything that's left in the same period. So anything that is left will be in the same period as the element we are trying to find. So we have the 5s2. There are 2 atoms, or 2 electrons in the 5s2. there are 10 atoms in the 4d10, and just again 2 when we get to 10 in the 5p. We will get 5p2. Alright, so I think that this is a little bit of a simpler form, a way to get the noble gas configuration. You basically get to cross out all this stuff, and you get to really simplify this. I'm not sure if I would expect you to be able to, label this chart with where the different orbitals are. I might make that itself a different question. If I label this, can you tell me where the 4s's are? Like that type of, where's the orbital in the periodic table? All right, so here is our noble gas configuration, and we're going to show why this is going to be useful just in a second. So why am I doing this? Why am I revisiting this and really making a big deal out of this? The transfer of electrons between atoms is the driving force for most of chemistry. Like, electrons are super important, like really important. We need to figure out which electrons are going to be transferred, how many, and why they are being transferred. That's going to tell us why certain reactions are happening, like why the sodium and the chlorine come together to form salt. So we're going to use this term here, valence electrons. You might have heard from this term from a previous science class, like 7th or 8th grade science. They are important, valence electrons. And I'm really going to hammer home this idea. This is one of the really important pieces of content for this class. Alright? Valence electrons are defined as electrons in the outermost energy level. When I talk about energy level, I'm talking about the principal quantum number n. For a 1s electron, this number is 1. 1s, this is 1. 5p, the number is 5. For a 5d electron, it would also be 5. Now, for most of the periodic table, if I can, nope, I don't have a, for most of the periodic table, what we're going to be talking about is what period it's in, the electrons. It's going to be this period. We're really going to kind of ignore the d electrons in terms of valence electrons. We'll talk about these d block a little bit, but not too much, because they don't really follow these rules. We're going to be talking about the s and the p blocks mostly. All right. So period 5, we're talking just the 5s and the 5p. For period 4, we're talking 4s and 4p. Those are the electrons that were going to be our valence electrons, if the element is in that period. So let me show you what I mean by that. Here's an example. Carbon. Here is our electron configuration of carbon. Again, I've done this. Valence electrons are only the electrons in the outermost energy level. Carbon has electrons in n equals 1 and n equals 2. Alright? The outermost is only n equals 2. N equals 1 is on the inside. They're called core electrons, and they're not going to do anything. They are going to stick there. They are locked in. They're not moving anywhere. But we now have these 4 electrons that are in the n equals 2 level. Okay? So we have the 2s, and we have the 2p electrons. So we have 1, 2, 1, 2. These 4 electrons are our what we call valence electrons. Okay? This is how many valence electrons carbon will have. And why I've been pushing this noble gas configuration this whole time is because when we do this, we get rid of the core electrons. We get rid of the junk. We only care about this. 2s2, 2p2, 4 electrons. These are the valence electrons. That's why I've been pushing this noble gas configuration so much, because it tells us how many valence electrons there are. I'm going to come back to just a small, slight example or exception, but I will talk about what I mean by that. Okay? So, nitrogen has 7 electrons. So we fill up 2s2. We fill up another electron. We now would have 2p3. And nitrogen, which has 7 electrons, would have 5 valence electrons. Just as another example. Alright, so here is 10. And here is our electron configuration that I had figured. This whole big long thing. Let's shorten it. All of this stuff right here are the core electrons. All that stuff gets shortened to the krypton. And we are left with just 5s2, 4d10, 5p2. So, how many valence electrons are there? Tin is in period 5. And if we go back a few slides, I could show that. It is in period 5, so we only care about n equals 5 valence electrons. We don't care about the 4d10. We have 5s2 plus 5p2. That gives us 4 valence electrons. Alright, we don't care about this 4d10 because tin is in the 5th period. We only care about the s and the p electrons. Alright, the reason why is weird energy stuff. I know that's not a good answer, but it's past the scope of what I would really like to get into for this course, because it deals with a lot of that like crazy math and quantum numbers and stuff that I don't know it. Alright, I'd have to learn that, and I don't want to do that. Alright. Oh, so if you notice something about carbon and tin, here is carbon, here is tin. They both had 4 valence electrons. I'm sure that's not a coincidence. They're in the same group. Big idea is, and I've underlined this to tell you how important it is. Elements in the same group have the same amount of valence electrons. And we will see that elements in the same group will have similar properties. Alright? It's super important idea of chemistry. And it is all due to those valence electrons. Just a fun fact that I've included. The creator of the periodic table, Dmitry Mendeleev, he does have an element named after him. It's one of those man-made ones. He was able to predict the certain elements that were not discovered at the time. He predicted properties such as their boiling point or their melting point. He was able to predict them relatively closely because he knew that they were in the same group. I think it actually was gallium or germanium, so 32 here, that was not discovered, but he was able to predict the properties of it. All right, I think it was gallium. So that's 31 over here. He was able to predict it. All right, so that is big important idea, and we can simplify this even more. Carbon, 4 valence electrons, as we have just seen. Nitrogen, you add up extra electron into the p orbital, 5 valence electrons. Oxygen, you add another electron into that 2p orbital, 6 valence electrons. You should be able to follow the pattern. How many valence electrons does fluorine have? I'm looking at you like it's Dora the Explorer. It's 7. Yay. Alright. Fluorine's got 7 valence electrons. If we were to include boron here. I wanted to swap these. Okay, that's alright. Boron has 5 protons. It would have 3 valence electrons. Beryllium would have 2. Lithium would have 1. And I've summarized all of this stuff in this picture. Alright. Arsenic. Group 15. The way you can do this is for the groups 1 and 2. That's how many valence electrons there are. So, cesium, 1 valence electron. Radium, down here, 2 valence electrons. For these groups here, you just knock out the 1. Like that. Arsenic, 5 valence electrons. Chlorine, 7. Thallium, 3. 3 valence electrons. And you may be wondering, where's the rest of the periodic table? I've mentioned this. We're going to talk about d orbitals a little bit. They don't have easily identifiable valence electrons because the d orbitals are weird. And I promise we will get to that. Alright. The last quick thing is Lewis dot structures. I have to change my camera again. This is not too much. It's pretty simple. All you have to do is take your element name. Here is carbon. Atomic symbol is C. It has 4 valence electrons. You circle them around the element. That's it. Nitrogen has 5. 1, 2, 3, 4, 5. You do the first 4, and then you're going to start to pair them up, and we'll see why we do this. It's important. It helps simplify something we're going to learn about in the future. I'll do another example. Oxygen, which we saw had 6 valence electrons. For our last slide. Here's oxygen. You go 1, 2, 3, 4, 5, 6. Actually, this should be here for being really, there we go. That's how it should look. Alright. That's all you have to do. So if we took tin, just as another example, we said tin had 4. 1, 2, 3, 4. Done. Alright. This is going to be helpful pretty soon. Alright, so, hello honors class. This is my, splicing ability that you're now seeing. I want to keep going with just one more thing. We're gonna, pick up the pace just a little bit. So, you can see I'm wearing a new shirt. We are different recording day, and I've spliced together these videos. So that's why the weird jump. I want to continue by discussing, noble gases. Just to kind of talk about them. We talked about noble gases in the context of electron configurations, and noble gases, they are in the elements in the group 18. So all the way to the right on the periodic table, we got helium, neon, argon, krypton, xenon, and radon. And I joked in class, but I did actually look up why they're called noble gases. And one explanation I saw, which I don't know if it's true, but I like it, is that they are like noblemen and noblewomen. They don't want to mix with the plebeian other elements. And what that means is that noble gases are what we would call inert. They are stable, and they don't react with other elements. They stand there and just chill. They're very just not reactive. They don't mix with other elements in the terms of, like, they won't react. They chill. And there's an important reason for that. Why? So let's start off with, they have 8 valence electrons. So if we go back here, all these elements here in group 18 have 8 valence electrons. Alright? And if we go back to neon here, neon completely fills out its n equals 2. So the 2s and the 2p, all of these elements, or all these electrons fill up these orbitals. So I talked about a full shell will give you stability, right? So neon here has a full 2p shell. That gives it stability. But it also has the full valence shell of all of the n equals 2 elements here. Alright, so not only does it have the full 2p shell, but it has a full 2p and 2s shell. This gives us kind of like a double stability. So we could call it super stability, whatever, but neon, it is super stable. It does not need to do anything because all of these electrons are filled. It doesn't need any more electrons. Why would it react and get more electrons? Because as we're going to see, electrons and with their transfers, what causes chemical reactions, and we don't need any more electrons. We're full. I'll talk a little bit about why some of the energetics behind this. That's going to be probably next week. We're going to kind of dive deeper into some of the energy bit of this. But so this is kind of like that introduction to this idea. But I believe in really getting to the nitty gritty. Why is this stable? Like, why is the full shell stable? Because I've said that concept, and I do want to explain it. Not now, but next week. And just to showcase this, when we jump up to n equals 3, here is argon. So the electron configuration of argon is to the right. I'll write this in. 3p is filled, just like this. But the 3s and the 3p is completely filled. So these are the valence electrons. Alright, we don't care about 3d because 3d is like all the way up here. Alright, that's too much energy. Be lazy. Don't worry about your 3d. 3d, we don't care about it. Alright, the valence electrons is going to be these 8 electrons here. And this is fold. So it has the full valence and the full 3p, which gives us super stable, and this trend continues for all of the noble gases. Alright. So, king me. What I mean by that, having a full valence shell gives stability, so other electrons want to be like that. Or other atoms want to be like the noble gases. They want to be like the kings that, have that stability. They want that. So they will gain or lose other electrons to have that same electron configuration as the noble gases. So when you gain or lose electrons, your charge is going to change. And I'm going to talk about charge and ions. I'm going to review that next week. I don't want to do it now. I want to give us some time to get some of the work done in class, and I don't want this to be go on for too long. All right, so for now we're just going to deal with it like this. Here's chlorine, and I'll write this in as well. Notice here, we are at 3p5. So we have 7 valence electrons. We have the 2 in the 3s, and then the 5 in the 3p. So 2 plus 5 gives us our 7. Alright, so in order to be like the element next to it, argon, in order to be like that noble gas, we're just going to take another electron and add it here. And I know they're using the arrows, but I didn't want to Microsoft Paint everything, right? So now, we added 1 electron, and now we have a 3s2, 3p6, and we have 8 valence electrons. So we have that double stability. Double stability. Alright, so chlorine, a chlorine with 1 more electron, which I'll explain it again next week, but chlorine minus is super stable. And it wants to be a chlorine minus. That is something that is energetically a good thing. What happens on the other end? So chlorine needed 1 extra electron to fill its valence shell. Let's look at sodium, which here is our electron configuration. To fill out its valence shell, so you would need, and I'm just going to write in, here's our 3p. You would need 1, 2, 3, 4, 5, 6, 7 electrons in order to fill this up. That's too much work, too much energy. Where, you know, why would you go through something that's going to be so supercharged just to do it? It it doesn't work. We're talk about why it's because of energy, unsurprisingly, but that's not. No, we're not going to do that. Instead, we're going to give away this electron. Goodbye. It's gone. All right. Then we will just have the same as the neon electron configuration. If we get rid of this electron, now we have the same electron configuration as neon, and we have that double stability here. We have that full 2 n equals 2 shell. We get our double stability, which means that sodium with a 1 lost electron, which will form a sodium plus ion, will be stable. So what I'll be asking you is, how many electrons does this atom need to gain or lose in order to be stable? All right, that's going to be our first, exercise for this. What I'm trying to get out of this. Next week, we'll start making that into ions. And this is something called the octet rule. A stable atom has 8 valence electrons. This is a rule of thumb, which means that it works in most cases, but there are exceptions. We're going to talk about some of the exceptions. I wanted to do it now, but I think I'm going to hold off just a little bit. We're going to talk about basically metals. So like for example, iron, like the D block orbital atoms, because when you include the d orbitals, things get all confusing because chemistry and reasons. There are other exceptions where you can have what is known as an extended octet, where you can do weird stuff. But this is a good rule of thumb, and we're probably not going to go too big into the details or the exceptions. All right. So here's chlorine. We have 7 valence electrons. We put this valence electron. Let's give it an electron, and now we have 8, and we are stable. So 8 is the magic number. Having this 8 electrons means stability. All right, and we're going to be using these Lewis-Dot structures to kind of showcase that. Makes things pretty easy. We now have 8 valence electrons, and chlorine minus here is stable. And the reason that's 8 is because when we talked about valence electrons, we talked about the s plus the p electrons of a given period. So let's just say 4s plus 4p. So there are 1, 1, 2, 3, 4, 5, 6, 7, 8. So we have those 8 electrons. That's where we get the octet rule from. All right, and sodium does something similar, where we take this electron and we just kind of yeet it over to the side. So now sodium would look like it doesn't have any valence electrons, but underneath, kind of hidden, we have those other electrons, the other 10 electrons. So in this case, there technically are still 8 electrons. That still has that configuration of a noble gas, but we just don't have any extra valence electrons, but this is still also stable. So having 0 electrons also usually means that we are pretty stable. All right. So you can probably see where I'm going with a lot of this, especially with what we talked about on Monday with the sodium chloride. And I will formally go over it just to have it, but I don't want us to go too much. I want to give you some time to do some work, some makeup work, and take this class relatively easy. And it's already probably around 30 minutes, so we're gonna take it easy. We'll talk about we'll get more into this. All right, we got a lot to get through, a lot of important, pretty cool stuff. So yeah, so you do have the homework for this chapter, or for this presentation. It's going to be homework 5. That's what it will be labeled. All right, so homework 5. It's going to be due probably Monday. The schedule's all been messed up. So all right. I'll just give you time to read everything here. All right, I'll see y'all later.